Hey everyone, my name is Matt Carney. I'm a somewhat recent graduate of the MIT Media Lab, and in particular, I did my PhD in the biomechatronics group. That's what's shown here on this picture. I've actually built pretty much everything you see there except for the carbon fiber foot. Uh, and I have a background in mechanical engineering and spent some time working in cellular solids and some self-assembly. And I'm really excited to be speaking to you today. The Atlas program is something that I think is really interesting and cool. And so I'm excited to kind of meet you all and chat about things. So I'm just going to jump right into it, and I'm going to show you some of the things that I've worked on over the years. This isn't everything, but it shows kind of a grouping from humanoid robots to bionics to what I originally used to call climate tech, but is really climate mitigation at this point. That's both renewable energy and pandemic response, which is turning into climate response as well. And if we have time, I'll chat a little bit about at least one of the art projects I've worked on in the past. I have others, but I prefer to remain anonymous on some of those. So let's just jump right into it. This project right here is Makhani Power. This was a crazy high altitude wind power company that is one of the most creative and innovative places I've ever worked. And I'll let them
Today,
speak
our
to it.
challenge is climate change. We cannot turn away from it. I absolutely believe that we can do something about it. That's what engineers are good at, solving problems, and this is a big one.
You very rarely work on something so open-ended. People believed in the audacity of it, in the individuals and their capacity.
All right, it's you now.
And this is actually the stage it was at when I was working there. We were actually to transition from these inflatable kites
You never
to the rigid
know
wing.
if you're gonna succeed, but one thing for sure, if you don't try, you're not gonna succeed.
And that's what I think is
It's
important.
not like one single idea that's gonna solve global warming. It's too big of a problem to be solved by one thing. It's gonna be the combination of multiple ideas from multiple people all over the world.
We got 5 minutes of autonomous flight down.
Is that really?
I don't know. Not in a row.
So that was, that was a fun team doing wild things. And what they're speaking of is really important. Like small teams of people are able to do really important things, but it's not just any one person is going to solve all these things. It's a massive group of folks. This is Mecca Robotics, where I went right after Makhani Power. This was actually a small team of five people building this robot. And for me, this was groundbreaking. It's the first time I got to work on a humanoid system. I'd wanted to do that since I was a child. And we were actually just got this thing working and shipped it out the door right after this. This is in the dog patch in San Francisco. And, I got to cut my teeth on this stuff, working on everything from the base up to the elbow, and then also the neck on Dreamer, which is this robot here. And I learned everything I knew at that point to like what it takes to actually build a robot, from the drivetrain to the electronics. Though I wasn't really doing much in the controls, but these robots are what introduced me to impedance control, and force control, which is really important for safe human robot interaction. And I built a number of different robots while I was there. In fact, I'm going to show you a handful of robots throughout this talk. Mecca was this tiny little team doing these amazing robots, but I was also working at Makhani Power and IDEO all around this time frame. Makhani was, as you can see, was these high altitude kites. This is the rigid wing. This is the first rigid wing that we were building. And I then went on to IDEO, where I learned about mass manufacturing and tightly integrated design, with taking industrial design and combining that with mechanical design to build things at high quantities, high volumes, with a lot of advanced technology. And I did all the internals in there. This is a robot I built for Songbei Kim's bio-inspired robotics course, which is all about under-actuated robotics, basically. So the motor is at the elbow, and it's free swinging around the wrist. It's trying to target the pink spots, or at least the top left pink spot is really what we're targeting. We didn't really have the objective avoidance of the other dots working yet. And this was a class project, so as you can see, it never quite works, but it's getting there. But it's a project I was really proud of. I ended up doing a lot of kind of heavy duty engineering on it. Right here is showing some components. I designed and machined all of this stuff. This is a compound gear, two-stage compound gear cable drive capstan to reduce backlash at the output, the backlash from the spur gear combination. And you can actually see the bearing stack here in this top middle picture. one of the things I did with this, I was able to rapidly produce this thing, was I used my master modeling approach that I learned at IDEO, which was, and I've adapted a little bit to the robots, where there's a lot more assembly of components and you need to release things at different points in time. But it basically draw a sketch to anytime more than one part interfaces together. And I then machined all the components, CNC machine, wire EDM. And in fact, that's what this video is showing, wire EDM running at the CBA shop at the Media Lab. And this is the Herco 5-axis CNC mill. It just shows, like, this is the kind of work I like to do. I like to run numbers, and I like to roll up my sleeves and get my hands dirty and cut some chips. And around this time, also earlier on at MIT, the kind of the first work I was working on was this thing called robotic assembly of discrete cellular lattices, or basically building giant things out of lots of little things. This is a concept that you can have robust assembly using this process. And built a lot of hardware, spent a lot of time on mechanical interfaces, exact constraint design in order to get components to assemble together. Because it's not just about building a robot that assembles, it's building parts that can be assembled by the robot. But at a certain point here, I was realizing that this stuff is really far out there thinking. And I wanted to do things that are more now, things rather than building things that could be a thing. I wanted to build things that are a thing. And that's when I realized that I needed to switch groups and focus again on things that really matter. And that's really what matters, is that in fact, I think we skipped here we go. I wanted to work on things that really matter.
What we are doing in our lab right now is, I think for the first time, truly the first steps towards building cybernetic systems, cyborgs. You know, we've been reading about this in our science fiction for years, and it's finally starting to get there.
My entire life, I never thought that I would be where I am now, having had an amputation. I have an opportunity to engineer my own body, and I had always dreamed about that.
The implications of making a seamless connection between the body and the robot means that we end disability.
But what is disability? I think that's something that I really started to wrap my head around when I switched over to this group. It's not just that disability is not just a physical disability. It's how we frame society around people. And it can be anything from, you know, it's not just like whether or not we picture a wheelchair as someone who's incapacitated or someone who's extremely able. It's that, you know, if there's not a ramp for the wheelchair, you may not be able to get through the door, say, to vote. And similarly, if there's not enough voting machines, you might wait in line for hours. And if you have an hourly job, you may need those hours to pay rent and be forced to leave the line before you had a chance to vote. Or for instance, your house may be in danger of climate-induced wildfires or flooding, and you are disabled by the fact that we have been guzzling gas for so many years, causing this climate change. This is all by design. Disability is by design, and design matters. And that's something that I've taken very seriously with my work going forward. Because it's not just that if you can come up with some idea for a multi-degree of freedom ankle. This right here is a 2-degree of freedom prosthetic foot. But you can see it also looks more like an anchor than it is a highly nimble device. And it could be that if you design it incorrectly, if you're not taking into consideration the people that are actually using the product. Because you really want something that operates like this, that is smooth and clean, as just an extension of the body. And sometimes that is as simple as just a simple spring. But the reality is that ankles are not pure springs. There is negative work that's done, and then there's positive work that is done. In fact, 50% of your forward motion during walking comes from push-off at the ankle. And a spring is able to store and release that energy, which is this dotted line here, but it's not able to provide that additional positive energy which is shown here as this displacement between the human ankle and the spring. And also shown here in this plot of the work done underneath this curve. You know, it's like why you get tired while you're walking, you're using your muscles. Well, we need to replicate those muscles. And a lot of people have been working on this for quite some time, where they've been combining springs and motors, and the motors acting like a muscle in order to drive a system, and the springs are acting like tendons to store and release some energy. And we've been trying to do that for years, but almost nothing has ever come to what you're seeing here, which is the ability to actually jog on a local system. And part of that is because there are trade-offs that are often made. And those are trade-offs that I wanted to challenge with the design of the prosthesis that I built for my PhD work. What you see here on the left is this ramp is an ADA compliant ramp that's at about 7.5 degrees. And what you see is an older commercial device that does not have dorsiflexion. And that means you cannot lean forward on your ankle. And that's really effective for being energy efficient. But as you can see, even on a simple ramp, it makes it difficult to have natural kinematics. It actually makes you unstable because you're having to compensate and lift your toe up, and you're not as stable as just bending your ankle to stand on a ramp. And what I wanted to build was something that could work smoothly and on a ramp, or even allow you to do additional tasks like kneeling down or standing on your toes to reach something up high from a shelf, or even to be able to go mountain climbing or something that is like you didn't even have access to before with one of these other devices. Because really, at the end of the day, we want to be building hardware that is, like I said, effectively seamless to the individual, as though it's an extension of the body. And in order to get that, you really have to drill down on the design specifications and the system design. So now I'm going to walk you through some of how I went through this process, identifying how to build a design, optimizing the design, and ultimately coming up with this design you see here. And so, I started with taking biological data, is like peak torques, peak powers, range of motion, and velocities, and also trying to understand at what kind of control bandwidth is required in order to achieve those. It's one thing to have a static torque, but it's another thing to have dynamic torque at that is controlled. And so I ran FFT on 1,000 gait profiles for knees and ankles scaled by mass and walking speed, and identified that for a 90 kilogram person walking 2 meters per second, they're going to need a closed loop bandwidth at 6 hertz and with capability about 73 Newton meters. That's the combination of frequencies and torques that get within 3 dB of the total energy provided during walking. I just want to look at equivalent body mass segments to make sure the thing is at least lightweight, at least equivalent to your leg, though you always want it as lightweight as possible. And from that, designed some target specifications. And this video here is taking us through kind of the making of, and I'm going to dive into deeper detail of this. This is just going to take you through this kind of a quick sprint through the entire process of 12 months of how we went from a blank sheet of paper to a neurally controlled device that provided walking.
The coffee smell of like
late nights.
Like, a year of late nights.
It was a year of many late nights. All of the nights, basically.
There's a whole lot of coffee smell.
So in this process, I was going back to first principles to understand how to model the series elastic actuator, how to design a spring to store the energy that my optimization spit out, prototyping with minimum viable prototypes in order to look at how I'm going to constrain the spring and store the spring, and then try to figure out how to package it all. Packaging is one of the hardest parts about robotics, is just figuring out how to fit all of this stuff in the smallest, lightest place you possibly can. And figuring out how to get all the parts made, how to source the components, building it itself. You should always build the first few of whatever you're making. You pound your head against all your mistakes. And then starting with bench testing.
There's a table for you. It's 30 Newton meters.
Providing some initial feedback, or gathering initial feedback from potential users of the device, just to even get the feel of it. And now in this case, I'm getting into testing out the finite state machine that takes it from heel strike to push off.
It's all virtual hard stops, so it's a virtual spring. It's a virtual parallel spring that is supporting you, and that little kick you feel as you lean far enough forward is going to go into powered planar flexion. Let's give you a little push off. Now, right now that push off is fairly low, and those are some of the parameters that we'll want to tune.
Mind if I swear?
Please.
Because this is fucking really cool.
That was pretty cool for us too. That was the first time anyone had stood up on the device. That was the very first steps on it. And you can see, so I designed all of the mechanical stuff, ran all these things, but it's really a team effort to get any of these things done. But so anyway, so that was kind of the overall process, but digging in a little bit more, what I was doing was I was using a process called kinematically clamped analysis. And what that means is I build a mathematical model of a series elastic actuator, which is my assumption of what I'm going to use, which means there's a motor, a drivetrain, and a spring. And I clamp the output to a desired trajectory of torque, angle, velocity. And I then feed that back through the model of the actuator and look at what the motor voltage and current is. And I then look to see what is feasible there. And I try to find, I try to do an optimization for an electric cost of transport, meaning I want to minimize the amount of energy per step that's being consumed by the motor itself. And then search through all of the parameters for the motor, gear ratio, and spring stiffness in order to achieve that. And that's, of course, subject to constraints based on motor limitations. Softer springs generally conserve more energy, but then your motor has to be moving faster. So there's all these trade-offs. And then also I made energetic maps to see where the design space is and see how tight or narrow those troughs are in that in those convex optimizations that we're doing. And so I looked at level ground walking as well as stair ascent and descent. I did that for knees as well and overlaid them to, and realized that there was actually a design space where I could achieve both knee and ankle kinetics and kinematics with the same drivetrain. And there is also optimal positions for those, but there is a place where a single system can work for both, which is fantastic from a lab maintenance and manufacturing point of view. And that's all well and good, but the numbers that an optimization spit out may not actually be realistic numbers. And the 9 joules of mechanical energy that the spring was desired to be was actually quite hard to do with the traditional coil spring that you see in most of the devices. And so I went back again to the first principles to understand what is strain energy? How do I store energy in a spring? And what materials are the best at that? And if you can take advantage of composite materials and fiber alignment, you can get very high specific energy densities. And leaf springs are pretty, a cantilever beam leaf spring is pretty good, but a cantilever beam with a moment couple where the entire beam is under moment bending actually means you're utilizing the entire length of the beam for energy storage. And you can see that by the shear moment diagrams here. And when I had that realization, I finally started to be able to piece all the pieces together, realizing that if I have this long spring, that fits well with a long screw, which allows us to have a high efficiency drivetrain. And that ended up becoming this thing, the reaction force series elastic actuator. What you see here, and why it's called a reaction force series elastic actuator, is that the dotted lines on the top are the output torque, and in this central picture here, you see the ground paths from output load through the axis of the screw, through the motor, through the spring, and then back to the grounding structure here. That means the bending of this beam is due to the reaction force of this drivetrain. And that's how I'm able to put all of that bending energy back into that spring. And you can see on the far left, there's a trade-off. There's a lot of sprung mass. The whole motor is moving around. And it also meant I had to get, in order to really optimize the design and package everything tightly, I had to get rid of all the extra couplings that you usually see in some sort of ball screw system and integrate the ball nut directly into the motor and swap out the bearings that are inside the motor so that it can take the high axial load. Rather than deep groove ball bearings, I went to angular contact bearings. And so I ended up getting custom motor, rotors, and stators along with the rest of the package. And of course, we also have to optimize the geometry of this linkage. So to put the power stroke in the correct zone of where our expected behavior is during walking. So we're able to run all those optimizations, and ultimately I came up with this package. It ends up being about 2 kilograms, which is very lightweight for a system like this. And there's even a lower weight combination of this if you offload that structure, where this can be integrated directly into, say, a humanoid robot or a quadruped or some other actuation type system. And this comes in at 1.3 kilograms, which is very lightweight considering the system puts out 175 Newton meters and well over 500 watts of power. And this design also allows us to easily swap out the springs. And that was the thing that was really exciting when I started converging on this design idea, is that flat plate, there's just 4 bolts that are holding in place. It means you can swap out the spring for different user mass So if someone weighs more or less, we can make the system more economically efficient for them, energetically economically effective. And we can also tune it for the ankle and the knee. You can think of it as like there's even a sport mode and an economy mode for this system that you could be tuning. And also I designed it so that the actuation can be personalized. We can swap out a ball screw that's specific for the knee or for the ankle. And again, get further optimizations. That's because the ankle is high torque, lower velocity, and the knee is lower torque and high velocity. And so we can take advantage of those things. That's not, it's easier said than done, because when you get into component specification, these are all defined by manufacturers, and they don't, it's not a continuous space. And that's what makes packaging in robotics really hard. It's not continuous. So put all the system together, start applying the controls. All of this is running on STM32F4. 427, I think, is the last model we ended up using. And then there's also motor driver built into this. This electronics package is built by a buddy of mine, Jean-Francois Duval, who has a company called Defy, and they do a lot of exoskeleton work. They were a spin out from our lab. This control loop is, I realized as I was making this presentation that this line should be off to the left just slightly here near the torque controller. And this is an older version of the torque control feed forward. Initially, it was just feed forwarding the gearbox, but I later went back and did system identification and put a model-based feed forward term in there, which has proven to be quite effective.
200 Newton meters, linear.
And this is the fixed rotor test, which is how you benchtop test the system. And this is actually with the original driver. You can see the motor is flopping around, the spring is bending. That was putting out 200 Newton meters of torque. And what we ended up seeing is closed loop bandwidth at about 6.2 hertz, which we actually were able to improve upon just recently. It turns out when I was going through this whole process, there was about, I actually had a mismatch between the motor inductance and the motor driver switching frequency, which caused there to be torque ripple at the high end of power, which was a real problem. And actually just in the last week or so, we're able to now get to last few weeks, we've brought online this new motor driver with field-oriented control, and we're now seeing 10 hertz closed loop control, which is really exciting, because that means the system's finally really hitting all the numbers I designed it to, and it means it's a very high performance system. And here you can see we're going through a frequency sweep, and I'm just gonna let it run all the way through because it's pretty aggressive and fun to see. And that like quick stop is showing you how powerful the system is. But it's not real power. You need output power to really understand, and that you can't do that with fixed rotor tests because you need motion. Now this is a kind of a hokey test. It's actually hard to do without just putting it on a person.
All right, that's 500. It was 500 watts.
But you can see here we're getting 500 watts output just by swinging this mass back and forth.
Swinging around like crazy. It's the technical term for it.
So, okay, so all that benchtop testing, then you got to put it on people. And like I mentioned earlier, I start off by doing a pull test, which is just a way to manually test the finite state machine, identify heel, strike, stance, dorsiflexion, control dorsiflexion, powered push-off, and swing. The thing is that's never real, right? You never really know until you put it on a person.
So it's a virtual spring. It's like
and so there's nothing like user testing. Like people say this, like if you're doing a startup or if you're doing any sort of product design, like you always need to be testing your customers and know who your customer is, know who you're designing for, and understanding that whatever you think they're going to do that and more things, and or different ways. And so these first tests on the device were really powerful for the development of the device. And of course, the academics want to see all the data. Again, this is when I had very high torque ripple on the system, so I expect the system to be much higher than this, tracking better as well as higher power. We're just starting to collect that data now. But even here, we were still getting within, actually performing a little better than my original simulations predicted, and partially that's just being overly conservative with efficiency terms in the overall system.
It's a game changer for disc golf when I'm coming through with the...
For me, it's not about the plots. It's about the person wearing the device.
let's see. Okay, so we can try to get you jogging on it, or actually, what would be really great is actually have you walk at a set speed on the treadmill for a minute.
For sure.
And you can see he's stoked on this, right? Like, he's never been able to walk on a device that has this comfort level and this ability to provide push-off.
Yep. That's cool. That's very cool.
Yeah. I was like trying to get a response.
Yeah, that was incredible. It feels way better than my blade for running, even just the quick jogs. But that fast 1.5, it's like a game changer pace.
Yeah, because you can
honestly
actually like, cruise around.
Yeah, because you're really feeling like, you know, like the energy return is just like powering you, you know? Not just, you feel like you're getting something back. It's huge. Yeah.
Okay.
Yeah.
Nice.
It's huge.
Awesome. So that's the name of the game, right? It's not just about, you know, I mean, it is about hitting all the numbers, but it's also about personalization for people so that they can, you know, apply their personality to the system they're wearing. So building actuators that are sized properly for bigger people and for smaller people. And that was part of the reason I built up this whole tool chain to go from desired output trajectories to design optimization of the device itself. That's a place I really want to dig deeper into my research, is how to really make it so that we can just kind of turnkey tune up a system to individuals so that they can have this. And that's why I call it biometrically derived actuation, which is like driven off of their own biomechanics that allows them to get a device that's the right size for them. So that when we finally reach this point where we have neural control, we can actually really provide what people are looking for. You know, there's part of me that thinks that all of a sudden we're going to get neural control faster than we thought, and then we need the hardware available in order to perform that way. And actually, there's a really cool documentary coming out just in a couple of weeks, February 23rd on Nova. This is a documentary about a new amputation technique our lab developed, and our demonstration with Jim, who you saw in some of these earlier videos. I mentored the development of this rock climbing ankle that kind of shows off the final design. So look forward to that. But what really inspires me with this work is that these devices, you know, for an ankle, you can get by with a spring, but above knee amputation are heavily affected by the currently available systems. There are no impedance controlled knees right now. And impedance control allows you to have this kind of stiffness, compliance. It's a much more natural behavior that you just can't get with the systems that exist right now. And you can see here, like I got to the point in my work where I built the system. There were some issues with this motor driver, and so we only got early testing with the knee. And then, of course, pandemic happened. But even just seeing this initial response with this person, you see the way he's playing with it, feeling it's such a new, novel feeling.
So you can lean into the ankle. You should experiment. You should be able to experiment.
Right. We also have a lot more information here because we have information from the ankle as well as the knee, even more so than just a passive system might have. And even without neural control, this is all just a finite state machine walking controller. But I had intended to continue as a postdoc working on this, and the pandemic hit, and I kind of accidentally launched into this effort.
The disposable respirator, we've been learning, is in short supply. And so the goal here was not to reinvent the wheel, but to source alternative media that could also satisfy the filtration requirements.
My name is Matt Carney, and welcome to my front porch. What we're trying to do right now is build a reusable N95 alternative mask. So that is a mask that is actually a respirator, so tight fitting, fits around your face, and can actually have all of the protections of an N95 mask. So that means it has a nice seal around your face, it is comfortable to wear for long periods of time, and it has a replaceable filter in it.
So this whole project, there's a lot more to all these videos, so please go back and check them out. This project started as a bunch of random people on a giant Slack channel. It was called Helpful Engineering. And it was just, you know, I think there were probably something like 50 or 60 people on this Slack channel. No one had ever met before. It was all fully remote. And it was a bunch of people who were trying to help. and people coming from different backgrounds. And very early on, within the first day or so, someone asked me to take lead, and I did, and I kind of organized all of the chaos of it so that we could deliver some real product. And in fact, we actually designed the entire thing in about 6 weeks, and all of the rest of the time since then has been figuring out, how are we going to scale this thing? Are we taking on money? Do we need to create a company in order to do this? What does it actually take to set up an ISO compliant quality system so that we can get through the entire certification process? And we've actually, dug deep into simulation. I worked with Dassault Systems to do some CFD analysis, computational fluid dynamics, to look at the effects of surface area in the filter, as well as residual CO2, which is one of the things that makes it hard to breathe through masks. And then we did iterative processing. We did I split this up into a modular design so that we could be doing both testing out face pieces as well as filter adapters all at the same time, and then converge on that. And we were testing this on real equipment. And at the beginning of the pandemic, a lot of people wanted to help, and so we were able to get support from different groups. This was Ator Labs in Florida, who helped. They're really great in doing a lot of testing for us. And we prototyped like crazy. This remote team. At some point, we were able to get together. We didn't get together until a year into this project or so. But we were prototyping, like in the top left, that is the modular locking mechanism. Just prototyping only the part that was necessary, and then also we took advantage of 3D printing of liquid silicone. We did casting, and then low volume injection molding, and of course 3D printing and whatnot. And we were able to bring all that together, and did a huge amount of user study with people to understand it. And then we've since scaled up manufacturing. We took on money. We raised about $700,000 to set up a manufacturing process in a clean room, following a full quality management system that we can then go and take towards to attempt to get certified. And we're now in that process right now. We actually partnered with the U.S. Army Medical Research and Development Command, who's helping fund our application to NIOSH. And NIOSH, again, is the N in N95, effectively, National Institute of Occupational Safety and Health. And we're really close to that now. We've been affected by supply chain, as everyone else has. But it's very close now, and it's really exciting to see. In fact, I was on a call with them just earlier today, just working out some of the details of how we're wrapping up the quality system, getting our application in. And so we went through all of that, but we also, didn't lose sight of the fact that, as I mentioned earlier, disability is about design. It's who are you designing for? And we really wanted to bring that into this entire design. We were looking at, making sure that our mask could fit as a child as small as a 3-year-old, all the way up to a large adult. And so we made part of this modular design was so that we could be swapping out face pieces for different people based on their needs. But also there was a realization that this goes beyond pandemic response. This is now a climate mitigation response as well. This is me in California on one of these very orange days from smoky haze in the sky. This is, at this point we're starting to see, and in Colorado you're seeing this, in California we're seeing this, the whole Northwest is seeing it, all the way up into Canada, Minnesota. And I think, unfortunately, we're going to be seeing more and more of this, that because of the impending climate disaster, we're going to have to be thinking a lot more about what it takes to be outside and how do we mitigate the response to this. And that's what ties this concept of adaptive action. This is something I think about a lot these days. What does adaptive mean? Is it adaptive technology is not just for disability. It's how do we reframe disability? It's how we all have access to have agency in our own lives in the world that's created. And that even gets into this. This is an art project, semi-subversive art project that I did a number of years ago. I actually was in Germany at the time, but I worked with some friends to actually make this happen. And what it is what we're looking at is a freeway in California that always has traffic. That's the red line here around, and has what once was a more barren hillside. This is now filling in a little bit more. And the idea was to plant the California state flower, the California poppy, which is against the law to be, or at least commonly known as being against the law to pick. So once you plant it, you plant a flower, it's there. And we wanted to write out the words impeach, just to have this kind of positive reinforcement of a political concept. And that's, again, getting back to this adaptive action, taking some sort of action in order to change the environment that we're in so that we can have more agency for ourselves. Because that's it's what we're talking about here. It's how we frame the conversation about what we're doing. And that's why I say, like, we need to build cool shit that matters to you, it matters to me, it matters to your neighbors and your community all around this world, because we're all connected in one way or another. And it all comes down to how we frame this to everyone else. And that's where this idea of adaptive action, where we can take action, we can take our superpowers as engineers to create and realize things in the world, and to make sure that we're doing things that really matter to people, that really have a positive impact in the world. And so if you want to follow more of the work I've done, I have a website. I haven't updated it since the pandemic. I've been extraordinarily busy. That video you saw of me talking about the mask response, I'm driving because I'm like driving to pick up samples or take samples somewhere. But anyway, you can follow me. I have more recent stuff on Instagram, of course, on LinkedIn. You feel free to send me an email. I'm into all types of creative works as well that are not just raw engineering. So please reach out, and happy to answer any questions. And I really appreciate the invitation to come speak to y'all. I'm excited about what y'all are doing out here. Thanks a lot.
Have a 10-minute hiatus.
Yeah, well, I jammed through that, so I go back and show some things. But it's kind of like overall, like I was kind of just showing, a lot of the projects I've had the opportunity to work on. There's more various bits here and there. I do a lot of being from the Bay Area. We have a lot of industrial arts, so I've gotten to have the opportunity to work on a number of those types of projects, various bits of fire breathing sculptures. And I'm a bicycle commuter, have been since I was a little kid. So there's also some bits of bike bits in there as well. Also, I'm a long distance hiker. I like to do big weeks long sections of the Pacific Crest Trail. And that's actually where I brought that mask with me. This is the mask here. I brought it with me this past summer, where I did another 240 miles. And there were actually a couple days where it was helpful to have. It's not great for walking uphill, though we actually have a new filter that's coming out pretty soon that has a 20% breathing resistance reduction that might actually make it better. But when you're out there and you wake up and it's smoky and it's getting hard to breathe, it'll help extend the hiking season, even though the views aren't very good when it's smoky like that.
Sure, go ahead. Oh, can you hear me okay?
Yep, I hear you.
Okay, thanks. I'm curious to just know more about, well, I really got close to the camera. This is the whole thing. Kind of what collaboration looks like for you, specifically beyond engineering, right? So are you working with sociologists, with manufacturers? Like, what do collaborations look like for you? And maybe what's the strangest one you've had that you might like to share?
Strangest one. That's interesting. Yeah, so collaboration for sure. I mean, just as a recent example, like these are the boxes for the mask. And I have a friend who's a product designer, actually packaging designer. So worked with her in San Francisco to actually design this. On this team, we also have it. So she's a packaging designer. We have a product designer and who specializes in user experience. And so we actually did a lot of studies early on in the process to see how people actually interact with putting straps over their head, and just this whole, and like thinking about like what happens if your hand is too big to actually be able to reach, or sorry, your hand is too small to reach over this gigantic filter. How do we accommodate for that? So we put little grips on the sides to try to make it a little bit easier. So yeah, so I worked at IDEO, and IDEO has this concept of the T-type person who has extreme depth, but also has breadth to have empathy for their neighboring disciplines. And I think that's really important, to have empathy for those disciplines. And that's where I've tried to work in a lot of different areas, so that I can recognize that like inspiration comes from unexpected places. And so it's really important to bring everyone to the table to kind of get these completely different points of view. I'm trying to think, like some of the engineering stuff tends to be just kind of driving deep down, but even on the bionic legs, some of the feedback you hear from women sometimes, or from a few women I've heard, is that most of these legs don't accommodate heels very well. You want to be able to change your shoes more regularly than just having your one pair of sports shoes. I like to take that into this design process. But like, for instance, in this example, I'm not a designer. I like to bring experts to the table and rely on them and trust them to make the right decisions to move forward. I think we should all kind of push back and understand, but bringing people to the table that have a completely different background is crucial to actually getting the best product out the door. What's my weirdest collaboration. I'm trying to think what is a goofy one. I am trying to think of one. That one's gonna have to maybe. I'm gonna have to come back to that one right now. Like,
okay. I think there's other questions too, so I don't want to hog it.
I worked on some weird things for sure.
Iris, you want to ask?
Yeah, I have a couple of questions. First off, fascinating presentation, really, really cool stuff. My question is a little bit about your journey, and I think you started to answer that partly with the previous question. So you were kind of tinkering in lab doing different things, and then I don't want to misrepresent what you said, but thinking like, well, I wanted to do something more meaningful. I'm not sure you said exactly that way. So then you moved to this biomechatronics lab. But how critical was that journey in the sense that you got to play with a lot of different things that gave you different experiences, and then you moved on to these prosthetics, right? Could you have done that straight off? Do you think that that was really informative for you to make kind of impactful decisions in the prosthetic domain? So that's my first question. I have another one that's much more engineering oriented, and I'll save that for when you answer.
Okay, hold on to that. Well, so the prosthesis space actually does come naturally to me. My mother is an occupational therapist, and my father's a scrap metal dealer. And so I do kind of, it's kind of like the perfect melding of all of these things. So like I grew up, going to work with each of them occasionally. Like I've been to my mom works in a long-term care facility where people are in comas and and learning to walk again. And, I purposely have gone with her to understand kind of like, what is the level of disability that people are dealing with? Like, and that's the thing, like this bionic leg is here in my attic right now, and it's not on someone. And that drives me insane. Yes, we can do all this cool work, but if it is just sitting, if it's not getting out to people, what's the point of all of it? Sure, it's inspirational, but it's also kind of a lie if we're not getting it, if there's not a path to get it out there to commercialization, to activation. And so that was, I think that was something that was starting to strike me. Like definitely that transition from cellular solids to bionics was realizing that in cellular solids, it's interesting work, it's cool engineering, there's a future path, but a lot of it is talking about a thing that could be a thing rather than doing a thing. Mm-hmm. And it's really important to me to do things also. And I've struggled with this. I'm even struggling right now with my career path right now. It's like, if I was like, I want to do engineering for good. I think most engineers want to do engineering for good. They want to use their superpowers to really do things to improve lives, but we don't always have the opportunity. My current day job is, I call it my pandemic job. I work at Amazon. I was offered the job on the second week of lockdown while I was doing the masks. And I didn't want to take it, but then but seeing the uncertainty, I was like, all right, I'll do this for now. And now I'm transitioning to what the next role is going to be, because that doesn't track well with my own philosophy of what I should be working on. But it's my own struggle to having gone back and forth with these things over those years, and looking back to the time when I was trying to do clean tech. I've been trying to do clean tech since my undergrad. My senior project was actually a tidal power system. It's my first patent application. And I went to Berkeley to try to do that, and ended up switching out and getting into the wind energy stuff, but got laid off and fell into bionics, robot or humanoid robots. So it's been this kind of like struggle to do good, but falling back into this robot space.
Right. I'm
not sure if I'm answering your question entirely.
You did, not the way I thought you were going to answer it, but you still answered it. It's still very useful. Thanks. I have a very engineering oriented question.
Please.
In looking at what you're doing, and you had some pictures where you're testing this, the prosthetics, and they're moving and vibrating, and I'm thinking about heat, and this is just my world in research. Is heat dissipation a problem?
Always. Yeah. I mean, it all comes down to the more current you can dump in that motor, the more torque you can get out of it. And that's
Is that a problem when you're attaching it to human, a limb, that isn't it a problem about heating up the tissue, and can it do damage?
Could be.
Yeah.
Yeah, it depends. So it could be, more, probably more so on an exoskeleton, probably. And I'll say that only because the motor is some distance away from where the residual limb is. So we do actually have that conduction path isn't super great. I've actually been interested in integrating with, so this is a fit socket. So this isn't the final socket, it's just polycarbonate, but normally it's some sort of carbon fiber. I've actually been wondering how we wanting to look into how well we can transfer heat through carbon fiber, and integrating some of that heat transfer into the system, into the device itself. Because you're absolutely right. These things, sockets are terrible. They get hot and sweaty. They're painful. I've actually done some work. I have one here trying to look at, can we start to switch over to some sort of textile-based socket liner interface where we kind of, this is just like a very early prototype I did of looking at switching around with like Dyneema and spandex fibers so that we can kind of build a more compliant system for transferring load to the body. And so, yeah, you're right. Heat to tissue is a real problem, but even just heat out to the environment, even that itself is a problem. In this, the power electronics, the motor driver is actually built in right here. And I use the aluminum frame as part of the heat sink for this. I have a conduction path through it to use the body of this as for heat dissipation. But things I've been interested in looking at are integrating heat piping into the motors themselves. I have some designs for fully encapsulated motors that can be fluid chilled. Use fluid as the heat transfer mechanism to get it somewhere else where we can then dissipate that heat somehow. Yeah, they're all major issues. You see, like, I believe a lot of the modern EVs are going to water cooled systems, just so you can be dumping more current in to get more heat out. But it all comes down to, like, then you're using using energy to run the pumps. So there are trade-offs to all these things. It's not always a win.
Fascinating. Thanks.
You bet. Anyone else?
I've got a question for you. What if students say, man, what you're doing is really cool, and how do I get into do the things that?
I get that question a lot, actually. Just, people see that. I mean, the Media Lab is good with their branding and the press, and so a lot of people get to see the work, which is why part of the reason we was able to show so many videos there. I mean, it's a good question. I think, for me, I've set up my career to try to understand all the hard things around this space. So the mechanical engineering, mechanical design, how do you build tightly integrated, robust machines, but also understanding like the limitations of power electronics and motor drivers. And I've actually found this back and forth between renewable energy and bionics to actually be really helpful, because it's a lot of the same things. We need high efficiency drivetrains. And so, like, something I often tell students who ask me these questions, like, it doesn't actually have to be a linear path, but you should be learning something along the way on each of those stepping stones, and with some, like, guiding star of where you want to get to at some point. And if you can take steps to learn and build up your skills, surround yourself by people smarter than you, that can help you grow faster and get to those points. That's what's worked for me so far. I also put a lot of hours in. That helps too. I like to put my headphones on and kind of dive in. Evan, did you have a question also?
Yeah, I had a quick question about the some of the safety systems for the bionic leg. I saw just like in one of the diagrams some of that, and obviously like some of the torque tests you were doing looked a little bit like, obviously that mode wouldn't be safe. And I was just wondering, like, depending on what mode the user is trying to use the leg for, would there be like safety systems that like impede movement in one mode, but then like would be really useful in another? And then also with the above the knee amputee, like some of that looked like a way more complex system. So I was wondering if you just talk about some of that.
Yeah, great question. So what I was calling out in the safety systems there, that's actually all the way down to the sensor level, is wanting to identify if we can trust signals to make decisions based on those signals. There isn't a lot of redundancy in the system, and so you need to know, like, is that joint angle correct? Is that a real joint angle? Is the wire connected still, or is it not connected? Is that load cell value a real value? Really, just like fundamental level, before we make any decisions about what the device is going to do, we need to trust that we are observing the device correctly. So that's that first step. And then, yeah, particularly when we get to neural interfacing, when we have the subjects that have some sort of EMG sensing providing input, we need to, again, make sure, one, that signal is a real signal, because if it rails one direction, in any of these, the sensor rails, it can cause the system to go into like maximum power mode, which can be extraordinarily dangerous. But also, to your point, like there very much could be different modes where you, and it's kind of defined by the finite state machine that we're using for the control. It says, if I'm, for instance, in swing, then I want to get into heel strike, and I'm not going to skip heel strike before going into push off, unless I'm in a running mode, in which case I want to be running off my toe and going from swing straight to toe. And so, yes, we do define these different modes and only allow you to pass through the modes in a certain order of operations, specifically so that we don't get to some weird state. And that's really important, like going into stair mode, because in stairs, if you go to, say you're trying to go down a stair and all of a sudden you go into this push off, you get pushed off down the stairs. And when it comes to the knee, that's much more important, because above knee amputees tend to have a lot of falls. The currently available systems, they're called microprocessor controlled MPC knees, are really not super great, because they don't always sense exactly the right thing that's happening. Part of that's because they're not talking to the foot, so they don't have that extra information. And so they can actually, like, often what will happen is it doesn't lock out when you're going for a heel strike, and it'll crumple underneath someone. And so they can actually be quite dangerous. And again, that's why I think the impedance controlled knees, I think, are still a wide open area for development and maximum value for people walking around with them. Certainly the feedback we get from people, even when they're just standing on the knee, before I've had this, like I said, I actually didn't manage to get that full knee walking controller going while I was finishing up the PhD. Even just that basic bit, people feel more stable just having a little bit of compliance rather than just dropping or not dropping or being locked out.
Awesome, thank you.
You bet. Yes.
Go ahead. So I think something that you mentioned previously is that, well, you said that you're not a designer. However, many of your work show like a high design level. So I'm wondering, I guess you interact with designers in your fabrication process, iteration process. So how do you navigate the challenges of just of language and to transfer your ideas, like from very engineered, like the engineered language to like talking to a product designer, like how do you navigate that?
Yeah, that's a good question. I mean, part of it is I do try to keep in mind the aesthetic in the design just as I'm going. Like for this leg, that was me kind of wailing on it, trying to be aggressive with the design, acknowledging that it's not going to be for everyone, but it's very clearly a robot, and I want and actually kind of write about this in my thesis, that like it's on us to take ownership of that design aesthetic and build something that people can, that it's like, I believe we shouldn't be medicalizing a lot of our stuff, because that then medicalizes people as well. And to build a design that actually speaks to, the strength and the confidence of both the device and the person wearing the devices is important. And so at the same time, I do enjoy working with actual industrial designers who have much better ways of describing these things that I'm not necessarily able to communicate myself. And so I don't know if I have specific languages other than an empathy for the field of industrial design. I think that's actually a really important part of the process. Some of the places I've worked in the past, we've had designers just on staff, even just to help record and communicate what it is we're developing, because it's not just the ultimate design. I actually think the process is important to tell people. That's why I made that video of the making of the TF8. That first video I showed from Makhani Power is actually put together by a woman, Andrea Dunlap, who's been doing that part of that storytelling since the very early beginning of that project. And I think it's really helpful to tell that engineering story, as well as find a way to actually communicate user needs to, user needs is kind of, that's like an FDA term for what you actually have to design in the end, but is like really important to actually build something that people can feel really proud of from that just kind of creative response to whatever that product is. And you saw that in the Mecca bot. The Mecca bot, we spent a lot of effort trying to make something that balances, like there's this thing called the Uncanny Valley in robotics, where something can be really cute until it's disturbing. It's like cute and getting more and more lifelike until it gets really disturbing, until you can get it so you can't tell the difference. And most robots are deep in that valley. And we try to stay before the valley of not being too human, not too scary, not too big. Like if you go to NASA, they have the Robonaut. They have the NASA Valkyrie robot, which I think is really beautiful humanoid. Before that, they built Robonaut, and Robonaut is gigantic. It is a beast of a robot, and that is really scary to be around. And all of those things are important to working with people that can help call that out and make sure that you're designing the right thing is really important. Because if you don't take that input, you might not build the right thing. And then that's a lot of wasted effort. I've actually thought about, so just one other thing is like, I think sketching is really, really important. I showed it a little bit in that video where I'm sketching things out, but it's not really showing it. I think that industrial design sketching should be part of curriculum for mechanical engineers so that they can communicate their ideas fully to people. I strongly believe in that. I practice, I watch videos on YouTube for like ID sketching, things like that to try to build up my skills, but I've never been formally trained in it. But I am always sketching out in kind of an isometric-ish view, just so I can kind of see things coming together. I do have some of my notebooks here. I can maybe even show you if you're interested, but I think it's really important. And I do that like early on, because then you can communicate with, like we do that on the mask team, where we have some industrial designers on the mask team that were helping us think through what that, again, what those interfaces were, how, like my daily driver is actually this bright pink one as opposed to this gray one, because I like to speak about the mask. Of course, I've been making it for a long time. These days, I still would rather not wear a mask at all. But the fact that we're building them and keeping people safe is important, because we get feedback from people. We get emails on this all the time of people thanking us for making the mask so that they can feel safe. And that wouldn't have happened if we hadn't taken in everyone's input. In fact,
sketchbook.
Yeah, you want to see it? I got it over here. I think this is. Oh, do I? Actually, maybe I don't have the real winner here. Where is it actually? This isn't the main one. Ah. Funny. I must have been showing it somewhere. There's one that I have, which is when I was doing all of the design work, really. And that one has all the sketching in it. I actually don't think this one has much in it. This is just little stuff. This one's more math, actually. So this one's not as much fun to do, unfortunately. Where is that one? Yeah, sorry, I called that out that I can show you, and then I don't, but here's some more stuff like, getting colors for bearing stacks. These are not my most fun ones, but just something to communicate.
Yeah, we saw some in the video, so cool.
Yeah, where are they?
Okay.
Now I'm concerned. That one's my favorite.
I need to find a number. Can we conclude?
Matt, one question. Is there like something that you haven't tried and that you're, oh, cool.
Just like interfaces. It's not the best.
Are there things that you haven't tried like in your research area that you are willing to do it like in this next chapter?
Oh yeah, are you kidding?
Like what are those things?
Yeah, I mean, there's tons of stuff I'd love to try, and that's, like to be a faculty member would be really awesome to have the opportunity to try a lot more stuff. I think that's what's so awesome about universities. You can take the risk. It doesn't have to be commercialized yet. Though I do think a path to commercialization would be really great for a lot of things, just so you can get it out there. I would love to expand on the textile wearable mechanical interface. I think that is still really unsolved. I mean, we see tons of exoskeleton folks starting to poke around at this space. There's a lot here that I didn't get through. I spent a month in Shenzhen at a textile manufacturing facility working on this, and I'd like to expand on that. And I think there's a growing interest in that. I also am interested in getting this device out to folks, but also experimenting with materials here. So there's a lot in materials, heat transfer, to Iris's question. I think there's actually a lot to be explored still in how we interface with these. I've been wanting to build this system out of out of different materials, like not just composites, but also wood. And I've been actually kind of really fascinated with wood and its energy storage capabilities. It's a really an amazing material. It's a cellular solid material and a composite, and actually has some of our, our wind turbine blades use balsa cores in them. They're designed kind of in a very similar process. But I'm also getting back over to that composite side. I've been exploring a lot of different composites manufacturing processes that I really want to explore to get into, seeing if we can drive down the price of turbine blades, or there's just a huge amount of wins we can get when we're not moving as much mass around. Mass, every time you accelerate and decelerate, that consumes energy, right? And so if we can build things that are lighter weight structures, then we can make energy savings there. And so that's kind of something I've been tinkering around with for a bit now. And actually a partner from the mask team has been working in the space for a bit, which is kind of what inspired me to start working on new braiding technologies, basically. And that, those are some of them. There's also, I've been thinking a lot about climate mitigation. As I mentioned, spending a lot of time when I walk hundreds of miles through the mountains, you see a lot of the impacts of climate, and it's like you have to focus, right? You can't do all of this all at once, but my background in clean energy, I'm realizing it's not just about renewable energy, it's about energy storage, and it's about climate mitigation. And I think it kind of opens the door to a lot of different things that we need to kind of evaluate. Like, is there technology that we can apply to reduce to work in forestry management, to kind of apply technology to help make it more cost effective to remove fuel from some of these fire zones? Are there ways that we can design habitats that are more resilient to some of these things? Like, in Boulder, you guys were directly affected by this recently. In California, we are all the time. Yeah, it's kind of a wide open space, but I would like to tie it to, I think in research, it's good to get wins along the way. And so so this is kind of like a roadmap of areas on the map that I'd love to explore at some point in the future. But in the meantime, there are paths to go, directly from the bionics. That's a working system that can be explored further. I'm a fan of building systems, rapidly iterating and de-risking things as quickly as possible, and getting wins along the way, but also putting a system together and then swapping out different components from that. And you kind of saw that with the mask build that allow us to kind of push limits on things. And so that mask, the filtration, all that stuff starts to get into what we're doing for our habitats in these new worlds where, air quality ends up becoming a really big thing. And maybe heat transfer becomes a thing there too. So that's a lot of stuff.
Yeah. Thank you for the wonderful talk. It's inspiring. Sorry for the interruption earlier. Thank you. And I think, our announcement do have your website so people can find you.
Yeah, check out some stuff. It's not as, I think I haven't updated it in the last year or two, so it's a little out of date, but Instagram,
but you are having enough cool stuff. I just keep spending time on it. Yeah,
check it out. There's some fun stuff.
I'll connect with you offline. Maybe we can put the two pieces of the talk together.
Yes, we can do that. Yeah. All right. Thank you. Bye.
Great. Thank you, everyone. Really appreciate it.